Hello everybody. Today we will have a tutorial session on material balances for reactive processes. We have looked at all the fundamental concepts which are involved in performing material balances for reactive processes. We have tried to solve calculations and problems which involved multiple reactions and also multiple units which had reactions happening. So today we will try to perform more example problems which will help us familiarize with the approach for solving material balance problems with reactions. Let us move on to the first problem. The company you work for produces alanine. Alanine is a non-essential amino acid synthesized by the body. It is important as a source of energy for muscle tissue, the brain and the central nervous system. Alanine also helps in the metabolism of sugars and organic acids. Alanine is produced in a reactor in a continuous process. There are two separate inlet streams that contain glutamine at 100 moles per minute and pyruvic acid at 50 moles per minute. The ratio of the molar flow rates of pyruvic acid in the outlet stream to that in the inlet stream is 0.6. So, the reaction is glutamine reacts with pyruvic acid to form alpha keto glutamic acid and alanine. Find the limiting reagent. What is the extent of reaction xi for glutamine and pyruvic acid? What are the fractional conversions of glutamine and pyruvic acid? Find the outlet molar flow rates of alanine, alpha ketoglutamic acid and any excess reactants. So, this is a simple single unit process with a single reaction. So, here it is a reaction where glutamine reacts with pyruvic acid to form alpha ketoglutamic acid and alanine, and we have also been given the molar flow rates for the reactants glutamine and pyruvic acid. So, we have also been told what is the ratio of the outlet to inlet streams for pyruvic acid. So, using this information we now need to calculate how much of pyruvic acid is actually consumed, what is the conversion, how much of glutamine is consumed and what is the conversion based on glutamine, and we should also calculate the composition of the exit streams and the extent of reaction. Let us go ahead and try to solve this problem. Based on the information we can draw this simple flow chart where we have two inlets and one outlet. The first inlet would be for glutamine and this would basically have a flow rate of 100 moles per minute, and the other inlet is pyruvic acid which flows at 50 moles per minute. You have an exit stream which would contain unreacted pyruvic acid, unreacted glutamine, the products ketoglutamic acid and alanine. So, this would be your product stream. So, now we need to first identify which of these two is the limiting reactant. So, the stoichiometric coefficients for both these reactants is 1. So, which means the ratio of the stoichiometric coefficients is also 1. So, here it is fed as 50 moles of pyruvic acid per minute and 100 moles of glutamine per minute. So, this means pyruvic acid is the limiting reactant and glutamine is being supplied in excess. So, the first aspect we have calculated. Now, the next thing is we need to calculate the conversions and the extent of reactions for the reaction using glutamine and pyruvic acid. So, we have the extent of reaction definition as moles of a component out minus moles in divided by the stoichiometric coefficient of that particular component. Here we are looking at the reactants which are glutamine and pyruvic acid, which means the stoichiometric coefficients would be -1. So, we need to identify moles coming out for glutamine and pyruvic acid to calculate the extent of reaction. We have been given that the moles of pyruvic acid leaving divided by moles of pyruvic acid entering is equal to 0.6. So, we already know the moles of pyruvic acid entering, which is 50 moles. So, the number of moles of pyruvic acid which is leaving the system as unreacted pyruvic acid would be 0.6 times 50, which equals 30 moles per minute. So, 30 moles of pyruvic acid is leaving the system per minute. So, the extent of reaction using pyruvic acid would be, so moles out which is 30 minus moles in which is 50 divided by the stoichiometric coefficient which is -1, giving the extent of reaction as 20 moles per minute. We know that the extent of reaction will be the same for any component in the reaction. So, the extent of reaction for glutamine should also be 20, but however let us calculate it and confirm that it is actually 20. So, how would we do that? We need to know the number of moles of glutamine which is leaving the system. So, using material balance for glutamine, we can write the balance equation as input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation. Glutamine is actually a reactant, so it is not being generated. So, you have only input, output and consumption. So, your output would actually be equal to input minus consumption. We know that the input is 100 moles, we have to look at what the consumption would be. Looking at the stoichiometry, we know that for every mole of pyruvic acid consumed, 1 mole of glutamine is also consumed. Therefore, consumption of glutamine would be equal to consumption of pyruvic acid, which is equal to 20 moles per minute. So, the number of moles of glutamine leaving the system would be 100 minus 20, giving you 80 moles per minute. So, hence we can calculate the extent of reaction for glutamine as moles out minus moles in divided by stoichiometric coefficient, which would be moles out is 80 minus 100 is the moles in divided by stoichiometric coefficient of -1, again giving you 20 moles per minute. So, this would be the extent of reaction using glutamine. As we expected, the extent of reaction is the same for when we calculated using glutamine or using pyruvic acid. So, the next aspect we have to identify is the number of moles of product and unreacted reactants which are leaving the system. So, we can write balance equations for the products. So, if we were to write a balance for ketoglutamic acid, it would be input minus output plus generation minus consumption equals accumulation. At steady state accumulation goes to 0, it is a product, so it is not consumed, it is not coming in. So, you would end up with output equals generation. So, using stoichiometry, for every mole of glutamine consumed, 1 mole of ketoglutamic acid is produced. So, this would mean that generation would be equal to 20 moles per minute. So, this would also be the output term. So, output would be 20 moles per minute. Similarly, for alanine, the output would be 20 moles per minute. The final product stream we have would contain 30 moles per minute of pyruvic acid, 80 moles per minute of glutamine and 20 moles per minute of ketoglutamic acid and 20 moles per minute of alanine which are leaving the system. So, this would be the exit stream. So, we also have been asked to calculate the fractional conversion of glutamine and pyruvic acid. So, conversion of glutamine would be equal to the number of moles of glutamine consumed divided by the number of moles of glutamine fed. So, this is 20 divided by 100, giving you a conversion of glutamine as 0.2 and conversion of pyruvic acid would be equal to number of moles of pyruvic acid consumed divided by the number of moles of pyruvic acid fed, which would be 20 divided by 50, giving you 0.4 as the conversion of pyruvic acid. So, with this we have solved this simple problem and we have been able to calculate all the parameters that were asked. So, let us look at another example problem which would be a little more complicated simply because it is from a biomedical system and the reaction is not given explicitly. So, we have already done problems similar to this. So, we will again try a problem here where the stoichiometry is not known, however, the generation and consumption terms have been given to us in an indirect way. So, the problem statement says one challenge in designing tissue engineered bone is the requirement that new tissue must be vascularized so that the cells in the new bone can obtain oxygen necessary for respiration. Hemoglobin in red blood cells bind oxygen for transport to the cells. Each hemoglobin molecule can hold 4 oxygen molecules. The hemoglobin concentration in whole blood is 0.158 grams per ml. Molecular weight of hemoglobin is 64,500 grams per mole. You need to complete a rough estimate for the oxygen consumption in bone prior to building an implant. Consider the femur as a steady state system with arterial blood flow in and venous blood flow out. What is the concentration of oxygen in the blood flowing out of the femur? The rate of the blood flow in the femur is estimated to be 34 ml per minute. Assume that hemoglobin is 100% saturated and the bone cells receive oxygen only from hemoglobin. The oxygen consumption of the femur is estimated to be 4 times 10 power minus 2 milligrams per second. So, all the information we need for the problem has been given to us. Let us see how we can solve this problem. The problem statement clearly tells us that femur can be assumed as a system with a single inlet and a single outlet, this inlet being arterial blood flow in and the outlet being venous blood flow out. So, we can draw a simple flow chart which would basically look like this. So, this is the bone and you have arterial blood coming in and venous blood leaving, and we have also been told that the flow rate of blood is 34 ml per minute and the blood contains 0.158 grams per ml of hemoglobin. So, this information is available to us. We have also been asked to assume steady state, which means the flow rate of blood outside which is leaving the blood would also bone would also be 34 ml per minute. So, now we need to identify how much oxygen is actually entering and leaving the system, and we have to calculate the consumption based on the information given to us. So, for this we would have to write an oxygen balance for this system. Before we start with the oxygen balance, we need to know how much hemoglobin is actually entering the system, so that we can calculate the number of moles of oxygen which is being carried by the hemoglobin into the system. So, for that reason we will first calculate input hemoglobin. So, we know that the concentration of hemoglobin is 0.158 grams per ml and the flow rate of blood is 34 ml per minute, which means the mass of hemoglobin which is entering the system would be 0.158 multiplied by 34 grams per minute. So, this would be equal to 5.372 grams per minute. So, we now have the mass of hemoglobin which is entering the system. However, we know that 4 molecules of oxygen are attached to 1 molecule of hemoglobin at 100% saturation. So, we need to know the number of moles of hemoglobin, so that we can calculate the number of moles of oxygen which is being carried by 100% saturated hemoglobin. So, for this we would have to convert the mass of hemoglobin to moles of hemoglobin, which we can basically do by using the molecular weight given to us. So, grams per minute divided by 64,500 grams per mole, giving us the molar flow rate of hemoglobin into the system as 8.329 times 10 power minus 5 moles per minute. So, from here we can calculate the number of moles of oxygen entering. So, input oxygen would be equal to 4 times input hemoglobin, because we have been asked to assume 100% saturation. We would just be able to do this, and the calculation would give us 3.33 times 10 power minus 4 moles of oxygen enters per minute. So, we also need to calculate the amount of oxygen which is consumed, so that we can actually calculate the amount of oxygen which would be leaving the system. So, oxygen consumed has been given to us, so which would be 4 times 10 power minus 2 milligrams per second. So, converting this to milligrams per minute, it would be equal to 2.4 milligrams per minute. So, we can convert the rate of consumption of oxygen in terms of mass to moles by using the molecular weight, which would be equal to 7.5 times 10 power minus 5 moles per minute. So, we are converting milligrams to grams and then converting grams to moles. So, this is the number of moles of oxygen consumed. So, now that we have identified the input and consumption for oxygen, we can write an oxygen balance for the bone, which would be input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation, oxygen is not being generated. So, output is basically equal to input minus consumption. So, output is equal to 2.58 times 10 power minus 4 moles per minute. So, this is the molar flow rate for oxygen which is leaving the system. To calculate the concentration of oxygen which is leaving the system, we would have to convert this molar flow rate into mass flow rate and divide it by the volume which is leaving the system. So, the volumetric flow rate is 34 ml per minute and the molecular weight is 32 grams per mole for oxygen. So, the concentration in terms of grams per ml or milligrams per ml would be 2.58 times 10 power minus 4 divided by 34, which is the volumetric flow rate, times 32, which is the molecular weight. So, this gives you a value of 0.242 times 10 power minus 3 grams per ml. So, this would be the concentration of oxygen which is leaving the bone. So, again we have been able to perform the required material balance calculations using the consumption term which has been given in terms of rate of consumption instead of stoichiometry. We have been able to identify the concentration of oxygen which is leaving the system. So, with this we have actually seen two different example problems where we have used single reactions and a single unit system. So, in the next problem we will look at something which is a little more complicated. So, this is the problem. So, here we have multiple reactions which are happening in parallel and there are also multiple units which are present in the system. So, let us look at this problem. To produce acetylene, pure methane and pure oxygen are combined in the burner where the following reactions occur, where methane reacts with 2 moles of oxygen to produce carbon dioxide and water, methane reacts with 1.5 moles of oxygen to produce 2 moles of water and 1 mole of carbon monoxide. 2 moles of methane is dehydrogenated to form acetylene and hydrogen gas. The gases which are exiting the burner are cooled in the condenser, which removes all the water. The gas leaving the condenser contains 8.5% acetylene, 25.5% hydrogen, 58.3% carbon monoxide, 3.7% carbon dioxide, 4% methane. This gas mixture is sent to an absorber where 97% of acetylene and all of the CO2 are removed with the solvent. The solvent from the absorber is sent to the CO2 stripper where all the CO2 is removed. The gas stream leaving the top of the CO2 stripper contains 92.5% carbon dioxide and 7.5% acetylene. The solvent from the carbon dioxide stripper is pumped to the C2H2 stripper where all of C2H2 is removed as pure product. Using the basis of 100 moles of gas leaving the condenser, calculate the ratio of the moles of oxygen to the moles of methane fed to the burner, calculate the mass of water removed by the condenser, what is the overall percentage yield of product which is acetylene pure based on the amount of methane entering the burner. So, now this is a much more complicated problem than what we have been looking at because there are multiple reactions and also multiple systems, Let us try to gather all the information and draw the flow chart for this system. The problem statement gives us that there is a burner to which methane and oxygen are fed. So, you have methane and oxygen fed to the burner. So, the reactions which have been stated happen within this burner, which is the reactor, and the gases which come out are sent to a condenser. So, in this condenser water is removed, all the water vapor which is leaving the burner is removed as liquid water from the condenser. The non-condensable components are then sent to an absorber. So, let this be the absorber, and in the absorber you also have a solvent. We have not been told what solvent it just is some pure solvent which is being fed to the absorber, and this solvent carries out all the CO2 and 97% of acetylene in the liquid form. So, this would be the solvent with the C2H2, 97% of C2H2 and all of CO2, and this solvent is then sent to a CO2 stripper. So, obviously there would also be gases, waste gases leaving, because other gases like carbon monoxide and other gases which are formed would also be leaving through the waste gas stream, because you have 3% of acetylene which would also leave through the waste gas stream. So, now this solvent which carries the acetylene and carbon dioxide is sent to a CO2 stripper, a carbon dioxide stripper, where you have carbon dioxide gas which is removed along with acetylene gas, and it has been told that the composition of this is 92.5% carbon dioxide and the rest 7.5% is acetylene. So, you have a liquid stream leaving which would contain solvent and C2H2 only, all the CO2 is removed in the gas phase. So, now you have a solvent which carries the acetylene, and this is then sent to an acetylene stripper, C2H2 stripper, where pure acetylene is collected as the product. So, obviously there will be spent solvent which is leaving the system. So, this would be the flow chart, and based on the information given we have to assume that the gases leaving the condenser, which is this particular stream, would be 100 moles. So, that is the basis we are supposed to use, and we have also been given that this stream is 8.5% acetylene, 25.5% hydrogen, 58.3% carbon monoxide, 3.7% carbon dioxide and 4% methane. So, we now have all the information that has been given to us in the problem captured in the form of this flow chart. Let us try to solve this problem. Based on the information given in the problem, we have chosen the basis as 100 moles of gas leaving the condenser. So, this is the basis, so which means this would be 100 moles. So, this particular stream leaving the condenser is 100 moles. Now, we need to identify how much of water is being condensed. We also need to identify how much of acetylene is recovered and also the ratio of methane to oxygen. So, the first part is to identify methane to oxygen ratio. How do we start for that? What would be the system we can choose? So, in many cases we have used the overall system to start with any calculations involving multiple processes, multiple units. However, here if we were to use the overall system, it can actually be very confusing because we do not have all the information about many of the streams. However, we can start with a different approach. The other approaches which we have used is either to start with the last unit or the first unit. So, here we could choose to use the first unit. However, we do not have the information about the exit stream which is leaving the burner. The information we have for the exit for this is for the gas stream which is leaving the condenser. So, the first system which we can choose would be for the burner plus condenser. So, this system we have information about the exit stream, we know the number of moles, we have the composition, we do not know the number of moles of water, but we know that it is only water. So, we just have to calculate methane and oxygen which is being fed, and using simple material balances this can easily be done. For the system chosen, which is the burner plus condenser, let us start writing the component balances. The first component balance we can write is CO balance. It would be input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation. CO is being generated, it is a product in one of the reactions. So, there is no consumption of carbon monoxide, there is no carbon monoxide entering the system, it is only methane and oxygen entering the system. So, your output is equal to generation, your output is equal to generation. So, we know that the composition of the stream has 58.3% CO. So, the output contains 58.3 moles of carbon monoxide. So, generation of carbon monoxide would be 58.3 moles. Similarly, we can write a balance equation for carbon dioxide, again input minus output plus generation minus consumption equals accumulation. Accumulation goes to 0 at steady state, there is no consumption or input for carbon dioxide. So, your equation again simplifies to generation equals output. We have information about output for carbon dioxide. It is told that 3.7% is the composition of molar composition of carbon dioxide in the gases which is leaving the condenser. So, generation of carbon dioxide would be equal to 3.7 moles. Similarly, we can write an acetylene balance. C2H2 balance would again be input minus output plus generation minus consumption equals accumulation. Accumulation, consumption and input go to 0. So, it becomes generation equals output, and using the composition of gases leaving, we know 8.5 moles of acetylene is leaving, which means that is the number of moles of acetylene which is generated in the burner. Now that we have identified how much of each of the product is generated from the reactions 1, 2 and 3 given in the problem, we can calculate how much of the reactants would have been consumed, and once we have the amount of methane and oxygen consumed, we already know the amount of methane and oxygen leaving, we can calculate the amount of methane and oxygen which is entering the system. So, this we can do by writing balances for methane and oxygen. So, let us start with the methane balance. So, again input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation, and we do not have any generation of methane because it is the reactant. So, you are having input minus output equal minus consumption equals 0. So, your input would be equal to output plus consumption. So, output we already know that it is 3.7, sorry, output is already known as 4 moles of methane, because 4% is the mole percentage of methane in the gas leaving. So, output is already known as 4 moles. Now, we need to identify consumption. Consumption of methane happens in all the 3 reactions. Methane is consumed by reaction 1 to produce carbon dioxide, from reaction 2 to produce carbon monoxide, and reaction 3 to produce acetylene. So, your consumption term would have 3 different consumptions: consumption 1, consumption 2 and consumption 3. So, looking at the stoichiometry, for every mole of carbon dioxide produced, 1 mole of methane is consumed. For every mole of carbon monoxide produced, there is 1 mole of methane which is consumed. For every mole of acetylene produced, 2 moles of methane is consumed. So, using that stoichiometry, we can basically calculate the consumption of methane as 3.7, which is the number of moles of carbon dioxide generated, plus 58.3, which is the number of moles of carbon monoxide generated, plus 8.5 times 2, where 8.5 is the number of moles of acetylene generated, because we have 2 moles of methane being consumed per mole of acetylene, we are multiplying it with 2, which is the stoichiometric coefficient. Thereby, we get the consumption of methane as 79 moles. So, input for methane would be equal to 79 plus 4, which is 83 moles of methane. Similarly, we can write oxygen balance. So, for oxygen balance, you would have input minus output plus generation minus consumption equals accumulation. No accumulation, generation or output, because we see that there is no percentage of oxygen given in the exit stream for from the condenser, which would mean there is no oxygen leaving. So, all the oxygen is consumed. So, input equals consumption. So, we now need to identify what the consumption is. So, the consumption for oxygen would again happen through the first two reactions. Reactions 1 and 2 both consume oxygen. So, you would have to identify the consumption of oxygen in the first reaction and consumption of oxygen in the second reaction. Using the stoichiometry of the reactions given, we know that for every mole of carbon dioxide used, 2 moles of oxygen is consumed. Similarly, for every mole of carbon monoxide produced, 1.5 moles of oxygen is consumed. So, this would be the consumption of oxygen is equal to generation of carbon dioxide times 2 plus generation of carbon monoxide times 1.5. So, the consumption is equal to 94.85 moles. So, therefore, input of oxygen is equal to 94.85 moles. So, based on this we can calculate the ratio of oxygen to methane fed as 94.85 divided by 83, which is equal to 1.143. So, this is the ratio of oxygen to methane which is being fed. So, the next aspect we need to calculate is the number of moles of water, the mass of water which is condensed from the condenser. That we can obtain using the water balance for the same system. For in this system water is crossing the system boundary. So, we can use the same system, which is the burner plus the condenser, for performing the calculations. So, let us write the water balance. So, the water balance would again be input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation and no consumption or input terms. So, your equation becomes output equals generation. So, we need to identify how much water is being generated. Water is generated by reactions 1 and 2. So, the generation of water would be equal to generation through reaction 1 plus generation through reaction 2. So, looking at the stoichiometry, for every mole of carbon dioxide produced, 2 moles of water is produced, and for every mole of carbon monoxide produced, there are 2 moles of water produced. So, this is 3.7 times 2 moles of water generated by reaction 1 plus 58.3 times 2 moles of water generated from reaction 2. So, giving you 124 moles of water which is generated. So, water output is equal to 124 moles. So, this implies mass of water removed or condensed would be equal to 124 times 18, which equals 2232 grams. So, the last part of the problem asks us to calculate the yield of acetylene, which is pure product based on the amount of methane fed. To identify this, we have to calculate the amount of acetylene which is leaving from the system. We already know the amount of methane which is fed. So, to get this pure acetylene which is leaving, we can choose a system which would basically have all the other components except the burner and the condenser as the system. So, when we choose this system, what we have is you have the gases, the mixed gases coming in, and you have waste gases leaving, and then you have carbon dioxide and acetylene leaving through the CO2 stripper, and you have the pure acetylene and spent solvent leaving. So, we are not interested in knowing any information about the solvent. So, we do not have to worry about what is the solvent or what are the flow rates. So, we just need to identify acetylene. Based on the information given, we know that the composition of this gas stream which is entering the absorber contains 8.5% acetylene. So, which means for the basis of 100 moles of gas, we have 8.5 moles of acetylene which is entering the absorber or entering the system chosen. So, the equation for acetylene, the balance equation for acetylene be input minus output plus generation minus consumption equals accumulation. So, here there is no accumulation because it is steady state, and there are no generation or consumption terms because the system we have chosen is a non-reactive system. So, the equation simplifies to input equals output. So, the input is 8.5 moles, which we already know based on the information given to us in the problem. Now we need to identify the different output streams. Acetylene is leaving through the waste gases. So, you have acetylene leaving here and you have acetylene leaving here and acetylene leaving here. So, there are 3 different output streams for acetylene. So, we need to identify how much acetylene is leaving through individual streams. How do we go about doing that? So, this waste gas has 3% of acetylene and this 97% of acetylene leaves along with the solvent. This has been given to us in the problem. So, this means acetylene in waste gas C2H2 in waste gas would be equal to 0.03 times 8.5 moles. So, this would be the first exit stream. So, now the next exit stream we have is acetylene leaving along with carbon dioxide from the CO2 stripper. So, the information we have is CO2 constitutes 92.5% and acetylene constitutes 7.5% of this stream, and we know that CO2 is not leaving the system through any other stream. So, all the CO2 which is entering would have to be leaving only through this stream. So, if we were to write a CO2 balance, we would have input equals output and the output would be only through this stream. Based on the information we have about the composition of the gas, the output would be 3.7 moles. So, 3.7 moles accounts for 92.5%. So, this implies C2H2 in the CO2 stripper exit gas would be equal to 3.7 divided by 0.925 times 0.075. So, this would be the second exit stream. The third exit stream is what we are interested in, which we can calculate using the material balance. So, let us write the material balance. So, we have 8.5 equals 0.03 times 8.5 plus 3.7 divided by 0.925 times 0.075 plus the pure C2H2 which I will call as P, and using this we can calculate P as 7.945 moles. So, that is the number of moles of acetylene product which is recovered. So, the yield for acetylene based on methane fed would be 7.945 divided by 83 times 100, giving a percentage yield of 9.57%. So, this helps this gives us all the parameters that have been asked for the problem. So, now we have looked at different types of problems where there are single or multiple reactions and single or multiple units, and we have looked at applying the same fundamentals associated with material balances, and we have been able to solve for all the required parameters. So, please practice more problems using the textbooks that have been prescribed, and that will help you understand the approach which is being taken for solving such problems. Thank you.